Alright guys, welcome back. In this video we want to solve this statically indeterminate beam using the three-moment equation. We want to be able to draw the shear force diagram, the bending moment diagram, and find the reactions. So you might recognize this, this beam actually if you've been watching my other videos. I solved this exact same problem using the slope deflection method. So if you want to compare and just confirm that you get the same answer either way, check out the description. I'll put a link to it down there, or also you can click up here on this bubble thing and that'll take you off to that video as well. But let's go forwards using a three-moment equation. So first of all, anytime you're doing a three-moment equation, look at each span that you have and draw the bending moment diagram for that span as if it was simply supported and carrying those loads. And then we want to go ahead and identify the distance of the centroid to the outsides of those spans and then also the areas under these curves. So if we think now about what the three-moment equation really does is it compares the internal moments, like three internal moments across two spans. So when we think about that, the internal moments at, we're going to have MA, we're going to have MB, and we're going to have MC. So MA is going to be an unknown right now, MB is going to be an unknown, but if we look at this and we think about MC, well, we can determine that the internal moment here is 0 because it's basically on the end of a span with a roller support there. So that is going to be 0. So if we write the three-moment equation ABC, then the first thing that we can do is notice that because EI is constant and EI is in every single denominator, that we can remove that variable from each term. And now what we can do is we can just substitute in all of the values that we have, and we're going to get this expression MA plus 4MB is equal to negative 437.5, which is good, but we have two unknowns and one equation now. So what we have to do is we come back up to the original drawing, and basically what we want to do is we are going to look at what's beyond basically this this fixed reaction. Is what we do is we imagine that we just virtually extend the beam into the wall here to some arbitrary point. Let's just label that point Z. You can label this point whatever you want, whatever makes sense to you. And the length that we extend into the wall doesn't actually matter, because what we're going to do is we're just going to assume that inside this wall, or basically beyond this rigid connection, that this section or this span is going to have an infinite moment of inertia, and you'll see that the length and everything else just cancels out. So what we want to do is we want to treat this basically as a three-span beam that goes this span is ZA, the next span is AB, and the next span is BC. So what we do now is we apply the three-moment equation across the spans ZA and AB, and then we're going to compare that, or we're going to generate another equation here. So let's go down here and we'll draw we'll write a three-moment equation for the span ZAB. So you'll notice there's some stuff in here like the area of ZA and the X bar of ZA, and we don't actually have that because we never drew that. We only have, let's go up a little further, we only have the area for AB and the X bars for AB and the area for BC. So we didn't draw a little bending moment diagram over on this side, but you're going to see that we don't actually need it, because if the moment of inertia IZA is equal to infinity, which is what we're going with, that means that all these EI terms for EIZA are going to be equal to infinity. And basically anytime we have infinity in the denominator of a fraction, then that whole term is going to 0. So this whole term here is going to go to 0. This term here also will go to 0. This term here goes to 0. And this is an important one because this is where we had a ZA and X bar ZA, so we don't need that. And another thing just to notice is that when we're talking about X bar AB in this case, we're always coming from the outside of the spans that we're looking at. So really, we are considering X bar AB right now to be coming from this side and going in, and X bar AB. But because this problem, because this load was right in the center, then these two are the same. Now, if this load was off center, then this X bar AB would be different than this one. So just be careful that you're always coming from the outsides of the spans that we're considering when we're using the three-moment equation. All right, so let's just rewrite this without these terms that we've crossed out. And because it's in every single denominator on both sides of the equation, then we can just cancel that out or just erase it. And we're left with this much simpler expression. So what we can do is we can just really fill this in: 2MA times LAB. That was 10. So this is 2MA times 10. Plus MB LAB, so MB times, that was also 10, and this was negative 6 times 625 times 5 over 10. And if we simplify this, we get, what do we have, 20 MA plus 10 MB, and that is equal to negative 1875. And then we can also reduce that just a little bit again, and we get 2 MA plus MB is going to be equal to negative 187.5. Alright, so now we have two equations and two unknowns, and you can either solve this by just simple substitution or using a 2x2 augmented matrix, and we're going to find out that MA is equal to negative 44.643 and MB is equal to negative 98.214. And those are the internal moments right at those reactions, basically at these points. So now we know we have MA, MB, and we already knew that MC was equal to 0. So I'm going to pause the video here, and we're going to finish off the video by drawing the shear force diagram, bending moment diagram, and finding the reactions in part 2. So guys, thanks a lot for watching, and I will see you in the next video where we finish up this problem.